So good morning, everyone. I'm Caterina Marinelli. I am a lecturer at the Edinburgh Napier University in Scotland, and I will present, as Professor Califano said, my work with Miss Cat Wright on the case study of Bellrock Lighthouse in Scotland, a work that is supported by the Northern Lighthouse Board. You may or you may not be familiar with the Scottish environment. Scotland has a rich cultural background that is actually supporting its economy as well. And within that structural heritage, stone has been a foundational building material for over 5,000 years now. Historically used for everything from prehistoric structures to Georgian and Victorian buildings. The country is often referred to as a nation of stone, and the structural heritage comprises diverse structures like castles, stately homes, abbeys, industrial buildings, as well as domestic architecture. Historic buildings in Scotland are protected by organizations and laws, and primarily through Historic Environment Scotland, which is the lead public body for the historic environment and also is an important research collaborator of ours. This time, we are presenting here a study that is relevant to the rich structural heritage of lighthouses. And the lighthouses are managed by the entity called the Northern Lighthouse Board. Scotland is renowned for its rugged coastlines, which are dotted with over 300 historic lighthouses. They have guided mariners through terrible waters for centuries, and by the nature of their role, lighthouses are often situated in some very remote places where they are completely exposed to the elements. So these lighthouses not only serve as a vital navigational aid, but also hold captivating stories of maritime history within the Scottish culture. So the Northern Lighthouse Board provide a vital safety service to mariners since 1786 and are responsible for the superintendence and management of all lights, buoys, and beacons within the Scottish and Isle of Man waters. So their service makes a significant contribution to the prevention of accidents and incidents around the coastline. And they safeguard not only lives and property, but also protect our precious marine environment. They currently operate and maintain 208 lighthouses situated in some of the most remote and spectacular locations. And their vision is to ensure an effective response to the climate emergency and the long-term future of the planet, while adapting to the impact of climate change is a core element of the NLB's strategic, tactical, and operation considerations. So via research and external consulting work, they have identified risks in particular areas, and they projected the significance of a range of scenarios of climate change upon their assets and upon their operations as well. So one such case refers to the average temperature and sea level change based on a worst case scenario and the strategic importance to mitigate its projected impact to infrastructure. So within that context, and according to the NLB's management framework, any future refurbishment should be including risk-based and data-based work programs. So improved inspection and assessment regimes will yield the required data to inform any future expenditures. that will lead to major works to restore an existing asset to its original capacity. So as stated in its future plans, the NLB will establish the current status of structural conditions and improve monitoring capacity to provide site-specific solutions, and will identify the wider risk interdependencies to mitigate risks posed by climate change. So to that aim, our role is to support the NLB, explore options for the development and effective use of numerical models for historic lighthouses. So we are going to talk about the case study of the Bell Rock Lighthouse, which is a landmark of civil engineering. It was completed in 1811. It is situated on a perilous reef off the Angus coastline, and it is one of the world's oldest surviving sea-washed lighthouses, standing 35 meters high in the North Sea, actually standing on the rock known as Bell Rock. It was built by Robert Stevenson of the renowned Stevenson family that has built around 82 lighthouses in Scotland. And its construction was a triumph of engineering in very harsh conditions. So the lighthouse's iconic design has inspired also other lighthouses in the world. So before that, there was no way of knowing that there was actually a rock below the surface of the water at low tide, and that was causing a lot of accidents in with ships. So it is a tapered cylindrical tower with balcony consisting of a copper dome roof mounted on a plate glass lantern. It is fixed to a masonry murette, mostly consisting of ashlar, granite, and sandstone. And the facilities that are housed there nowadays include batteries, engines, solar panels, overnight personnel accommodation, workshop space, bulk fuel oil, and water storage. And as you might probably already have guessed, owing to the scale and logistical challenges of any future major upgrades, these would constitute a long-term operation. So the steps followed to create a reliable numerical model for the Bell Rock Lighthouse were far from easy, with data collection being particularly demanding for the geometry of the structure, the materials, and for the environmental conditions in the area. So valuable sources of information had been the original design drawings in Stevenson's account that was published in 1824, historical wind data from the Met Office archives and currently working meteorological stations in the area, and also wave monitoring buoys in the North Sea. So a numerical model was developed using the finite element software Abacus, adopting a mesh of quadratic tetrahedral elements. Masonry was modeled using a continuum homogenized approach. And the material properties were an adaptation of what we could find in the literature, adapted to historic data from local quarries where these materials were sourced from. We used standards and well-established methods in the literature to derive wind and wave loading, which together with the live loads that were given to us by the NLB formed the load combinations that we used for a range of loading scenarios. So the output was evaluated in terms of resultant reactions, stresses, and deformations in comparison with the macroscopic response patterns and data from similar structures in the literature. The numerical model is useful in providing original data with respect to the computed displacements and stress states along the height of the structure. And these worked in a complementary way to analytical calculations and the assessment by inspection, as far as this is possible, of the current condition of the lighthouse. So the first basic scenario that we are presenting here evaluates the response of the lighthouse under dead and live loads from the facilities and equipment only. The vertical normal stress distribution reveals that the sandstone areas of the structure's main body experience the highest compressive stresses, but the level of stresses everywhere is smaller than the intrinsic strengths. So we can see also the displacement distributions that appear as expected as well, with the largest vertical displacements with the top layers and the horizontal ones around the locations where spaces for the rooms are situated. Then we proceeded to a more realistic loading scenario where we included wind and wave loading. Both were applied as pressures, the wind over the full height of the lighthouse and the wave loading corresponding to a significant wave height of 10 meters. Results for the combination of wind and wave loading show the highest stresses in the vertical direction are located where the wave makes contact with the structure, and in the horizontal direction loading is fairly similar to that of wave alone. An area of tension occurs at the base of the side where the wave impacts, and we have higher compression up to the breaking point of the wave. It should be noted also that we didn't have any visual studies of where the waves do break on the lighthouse, so the height of the impact has been reasonably assumed. The horizontal displacements are dominated by the direction of the loading, and we observe the largest values around the areas of the rooms, again within the sandstone regions of the lighthouse. So to provide a structural assessment of the Bell Rock Lighthouse under the loading scenario that was considered, we examined three possible failure mechanisms. So based on the stresses as shown earlier, the stress state of critical points was checked against more Coulomb envelopes suitable for the two materials, and we confirmed that they are well inside the safe zone. Failure due to overturning occurs if the destabilizing moment due to the wave impact is higher than the stabilizing moment, as provided by the self-weight. And with the assumptions considered, the 10 meters high wave, a safety factor of 2.4 was established. And as far as sliding is concerned, where we checked what is the relationship between the horizontal force induced by the wave with respect to the frictional force that exists at the interface between the lighthouse, the base of the lighthouse, and the reef. Again, we defined a safety factor of 2.5. So with the current situation, and the loading scenario that we considered, we confirmed what is actually the current situation, which is considered as satisfactory and without needing any major interventions at the moment. So with our findings, though, we also established the need for a wave load parametric study, given the criticality of the wave loading for the lighthouse. So the next steps for this research would be to actually determine which wave would produce cracking, which wave would destabilize the lighthouse. So the results obtained so far constitute a successful pilot study for the Bell Rock Lighthouse. We developed a three-dimensional finite element model, and safety was verified against these three examined failure mechanisms for certain adopted loading scenarios. And apart from a parametric study of wave loads, which we already stated as a future aim, we also consider working towards implementing more detailed material laws and investigating mesh sensitivity and alternative boundary conditions. These are all critical steps, not only for considering our research focus, but most importantly, because they have value, they have applicability for our collaborators, for the Northern Lighthouse Board. Firstly, for the identification of critical areas for structural health monitoring and interventions, and also longer term for an adaptive approach to risk scenarios due to the imminent climate change. So thank you very much for your attention.